Now, let's look at some ways we can combine relations. And the idea is basically that, well, we'll see that we can combine them in some ways that will remind you of sets, and we will combine them also in some ways that will remind you of functions. So let's start with the first one. By definition, a relation is just a subset of A cross A. So we can use set operations on them. So, for example, union, intersection, difference, etc. So just to give a couple quick examples of these, let's consider, consider relations R and S on the integers. R is congruent mod 4, and S is congruent mod 5. Then R union S, how can we express this in these terms? R union S says elements are related if they are related in R or related in S. So as we've seen before, union acts as a sort of logical OR type operation. So congruent mod 4 or mod 5. So, for example, 10, 14 is in R union S because these are congruent mod 4. 10, 15 is also in R union S because these are congruent mod 5. But, you know, what's an example of maybe 10, 16 is not in R union S, because it is not congruent mod 4 nor mod 5. So let's give another simple example. R minus S is, so we are saying elements are related if they are sort of contained in the relation R, but not contained in the relation S. So if they're congruent mod 4, but not mod 5. So for example, 10, 14 is in R minus S, because these are congruent mod 4 and not congruent mod 5. 10, 15 is not in R union S, or sorry, is not in R minus S, because these are not congruent mod 4. And for example, 10, 30 is also not in R minus S. These are congruent mod 4, but they are also congruent mod 5. So they are disqualified by being also related in S. And one final example of this, R intersect S, congruent mod 4 and congruent mod 5. If you remember your Chinese remainder theorem, this is the same as saying that they are congruent mod 20. So here's a nice little example where you can intersect some relations and get a new relation that you also have a name for. Very nice. So basically any set operations that you can do on subsets, you can do on relations because they are just subsets of this set. But we can also define a sort of composition of relations the way you would define a composition of functions. So how do we define this? So R and S, let's say they're still relations on A. The composite, well, let me just write that. R, S, relations on A. The composite, S follows R, so it uses the same notation as the function case. Oopsies. Is defined by xy is in S follows R. Excuse me. If you can get the pair x comma y by relating x to something in R and then relating that to y in S. So xy is in S follows R. If there exists a z in A such that x is related to z by R and z is related to y by S. So S follows R is sort of, again, chaining together these relations R and S, and as we will see later, it does have to do with transitivity for that reason. And we can also define powers of a relation. So if R is a relation, then R to the n is just the relation given by composing R with itself n times. So let's look at some examples. Let's consider the relation R, which is congruence mod 4, and S, which is the relation less than or equal to. And let's consider these as relations on the integers. What is the composition? It consists of pairs x, y, or let me say x is related to y if there exists a z integer such that, let's see, so we first perform x related to z, so x is congruent to z mod 4. Then we say that z is related to y in S, so z is less than or equal to y. And let's think for a second about what this is saying. Is there a number less than y, or less than or equal to y, that is congruent to x mod 4? And we know that there are infinitely many numbers congruent to x mod 4. They happen every fourth number. So you can always find one that is less than y. So you can always do this. Which means that S follows R, the composite, I should underline that, is the trivial relation Z cross Z. So it is the subset which is equal to the full set, meaning every two elements are related. So it's kind of a trivial relation. What is s squared? Well, it is pairs x comma y such that there exists z with x less than or equal to z and z less than or equal to y. And this is basically saying that x is less than or equal to y still, because we know that these two conditions together mean that x is less than or equal to y, and if x is less than or equal to y, just take z equals x, for example. So this is the same as saying that x is less than or equal to y, which is to say that s squared, the relation, is equal to s, the original relation. And it is a fact that, so this is basically coming from the transitivity of s. So in general, the relation R is transitive if and only if R to the n is a subset of R for all n at least 1. So taking compositions is essentially chaining together copies of your relation. And so you expect this to be related to transitivity, and it is. The relation is transitive if every power of R is a subset of R, which essentially boils down to saying that if you take a chain of relations, they are still related. And it is a nice practice problem to show that they are not always equal, but they can be, R to the n can be a strict subset of R. So it's good practice to try and find an example of that.